All right, we're kicking off section 7.7, approximate integrals. And to be clear, what we're actually embarking on is a really interesting branch of math that we're going to call numerical quadrature. Quadrature is a historical term that just means finding an integral. So our objective in this video is to introduce the fundamental problem of numerical quadrature and the techniques that we're going to develop for approximating integrals. So our task, as it has been really from the beginning of the chapter, is we're given some function f, either analytically or as a data set of the form x sub I, f of x sub I, and we're just going to suppose we have n of them. Okay, so x sub 1, f of x sub 2, x sub 2, f of x sub 2. So just data points, pairs. We seek the value of, and I'm going to call it capital I, integral from a to b of f of x dx. Okay. Now, if we're given it analytically, then our typical approach here would be to find an antiderivative, which is what we've been developing in the last 6 or so sections, right? And the x sub I are chosen from a to b. They may or may not be equally spaced, but if we're given the choice, we're going to equally space them, okay? So we'll talk about that in a second. But we have two basically, complications, right? Which is, one, the antiderivative capital F, right? That we would have to calculate. I is capital F of B minus capital F of A, is complicated or hard to find or to work with. So it would just maybe it just takes too much time, right? And it would just be easier to do something else. 2, maybe it's impossible to do this because the antiderivative capital F cannot be expressed using elementary functions. So we've already encountered this before, where we said that, so for example, the function little f of x equals 1 over square root of 2 pi e to the negative x squared over 2 does not have an elementary antiderivative. We cannot express it in terms of elementary functions. So this is an instance where if we wanted to find the integral of this function over any interval, we'd have to resort to a different technique. Right. So what we're going to do then is we're going to approximate. So approximation of an integral, which, by the way, I keep saying integral. We mean definite integral, okay? So this is specifically the task of finding the definite integral of f of x from a to b. So we hope to find some procedure that involves f, or the data points. We hope to find some I sub n where I sub n is close-ish to I, which is the integral from a to b of f of x dx. Okay, when we say close-ish, we define, or we mean, so there is some error, e sub n, where the integral, the thing that we're actually looking for, I, is this approximation plus this error, okay? So our estimate, our error. And we hope that the error is very small, right? We hope that it could be as small as possible, even though it could be positive or negative. We'll see examples of both. So what we would consider a good approximation or a good approximation procedure allows, given some tolerance, epsilon, we can make the absolute value of that error term to be less than epsilon using a sufficiently large number of data points n or partition points, right? So we'll get into that in a second, because one of the fundamental challenges here is that there's a trade-off, right? So the better approximation, the more energy, time, computation we may need to involve. So if you think about it as a spectrum, and it's not perfect, right? There's, it's not really a perfect trade-off between the two. Sometimes we can get a really good approximation, even with a small number of sample points. But in general, if we're talking about a bad approximation or a good approximation, right? That means we're making a trade-off between how easy it is, right? Easier, harder. And I mean that, in the sense of whether you're doing it by hand or you're using technology, it'll take more time, more effort. And in the context of more direct applications, it may also literally translate to more money involved, right? Because you need to use a perhaps supercomputer to really run these calculations to a degree of accuracy that you want. But that maybe makes it more accurate and less accurate, right? That's what we mean then by good or bad approximation, right? So there's kind of a trade-off, and you kind of have to decide, I kind of want to land somewhere where I get a good enough approximation for my standard without spending too much effort. So we'll talk more about that later. For now, we should talk about the techniques, because we're going to talk about a few different methods, algorithms. And these are written sort of in order from least complex to most complex. But we're going to have a separate video for all of them, okay? So we have the endpoint approximations. There's two of them. So there's the left endpoint approximation and the right endpoint approximation. We're going to call capital L sub n and capital R sub n for left endpoint approximation and right endpoint approximation, respectively. And these are really cool. They're built really from our Riemann sum construction. So it's like almost we've already done this, right? And we'll see how they play out. There's the midpoint rule approximation, which we will denote capital N sub n. Notice that I'm putting subscripts here that are little n. That's because if we think about them in terms of, so in practice, we sometimes use this in an iterative fashion. So iterative means to repeat. It really means we're going to subdivide our interval A to B using n subintervals. And typically, we're going to pick some ideal n that's big enough to make the approximation really accurate without being too much work, right? So n, the interplay between n and how the error term change is a really important part of this. 3, we have the trapezoidal rule, approximation, which we'll call T sub n. And lastly, 4 is the Simpson's rule, approximation. This one's named for a mathematician whose last name was Simpson, not for The Simpsons, the TV show, which I don't think is relevant anymore. I think, are they still making that one? I don't know. You ask any purists and they'll tell you after season 10, it all went downhill. Okay, others exist, for the record. There are other approximations that we can use. They're beyond the scope of our course. So really, this whole section is our very brief introduction to the wonderful world of numerical analysis. If I have any math majors in here, you may take or have to take numerical analysis at some point, especially if you're going into applied math. All right, so our toolbox, let's talk about that. So I'm going to demonstrate a lot of things using, by hand, but you can use a pocket calculator. So you can use whatever calculator you have on hand. Maybe your TI calculator, maybe your phone calculator, right? But you can use more sophisticated technology to make these calculations real quick. So for instance, you can use spreadsheets, like Excel and Google Sheets. These will work. In fact, I'm going to link at the end of these videos a couple of spreadsheets that you can use, that you would just have to copy it to your personal Google Drive, and then you can play around with it and see how the calculations play out. But that'll do like all the calculations at once, and it'll allow you to use a pretty arbitrary precision. You can also create small scripts in a programming language of your choice if you are if you've already used some programming languages in the past. I don't know, this isn't a requirement for this class, so of course it's not a requirement for you to know how to use this, but at the university level, if you go on to take numerical analysis, you will need to use a programming language that they'll have a few of choices for you, but the common ones are Python. Python is really easy to work with, C++, or MATLAB. But MATLAB, for the record, is proprietary. You have to purchase that. If you're, again, just like I said earlier in a different video, if your university has a license for MATLAB, you could probably just use a computer lab there. But these are the 3 typical languages that you could be asked to reproduce some of these algorithms in. And it just makes it easier. You just, write the code or find the code somewhere, and then it'll run the calculation in like seconds, right? As opposed to doing it by hand, and it takes a lot more time. So this can be memory intensive though, so just keep an eye out for that. In the next video, we're going to illustrate all these ideas